remember in geometry when you learned about convex polygons? I mean, you might not remember what a convex polygon is, but remember that you at least heard the term convex and then non-convex polygons. Okay. We're going to talk about something kind of similar to that, and it has to do with curves. Polygons all have straight edges. Okay. For a curve, we talk about concavity, right? Whether something is the type of concavity that it has. All right. So let me define it algebraically, and then I'll draw you pictures of it visually so that you can see. Okay. Concave up. A function is said to be concave up when the second derivative is greater than 0. That is called concave up. Let me draw you the simplest concave up equation that exists, bless you, and that's a parabola. That is called concave up. All right, you think it's almost like something that could hold water. A little bit, you could consider that as maybe the option. All right, so then we have concave down. Concave down is the reverse, and that is when f double prime of x is less than 0. And so concave down would look like maybe a parabola upside down, where nothing would be able to gather, no liquid or anything could gather in that. So what haven't I covered? Well, not necessarily sideways. That would not be a function. It would fail the vertical line test. But I've got greater than 0. I've got less than 0. Okay, so what happens when it's equal to 0? All right, and the answer is nothing. Unless there's a change, just like we saw on our first derivative test, where something changed from positive to negative, then we have something. Okay, all right, so we'll talk about that in just a minute. Let me draw you another visual. Take sine, for example. All right, what is continually happening in the function of sine? Okay, is the concavity staying the same? No, the concavity is always changing. Okay, so at the beginning of this function, what kind of concavity is it having? It's going with a curve like that. Okay, so that has negative concavity. Okay, we say it's concave down. All right, then it switches to concave up. The switch happens about right here, and now that piece is concave up. And then about right here it will switch again, and then it's concave down, and then it switches again to concave up, and then concave down, and then it just continues to cycle back and forth. So this section right here, whoa, where'd you go? Come back. This we call concave down. And then the next section in here is considered concave up, or positive concavity. And then we've got concave down, which is negative concavity, and this continues to switch and switch and switch and switch and switch. Okay, all the places where it switches has a name. So all of these are called inflection points. Have you heard of the word inflection in any other context? Okay, where? Like, where have you heard of inflection?
Like speech.
Okay, give me what do you mean? You're exactly right.
Like if you have a speech inflection, like it's like a really odd.
Okay.
Global thing. Like it could be like a list, or it could be an accent.
Okay, so if you have an inflection, it means you're speaking with maybe changes in volume. Like you get really quiet for emphasis, and if you get really quiet, or maybe you get really loud for emphasis, or you're changing the dynamic of your speech. Okay, we call that the inflection of your voice. Okay, some people speak in monotone and it's really boring and they have absolutely no inflection because it just stays the same all the time, as opposed to other people who have a lot of change in their voice. Okay, that's an inflection point. So inflection usually means a change in something, and so this is a change in cavity. All right, let's do a couple examples. find the critical points and inflection points for the following. And the function is y equals 2t cubed minus 14t squared plus 22t minus 5. We want to find the critical points and the inflection points. So we're going to do both the first derivative and our process of setting it equal to 0 and undefined, and the second derivative and the process of setting it equal to 0 and undefined. So you're applying that same process now to both the first and the second derivatives. So our y prime is 6t squared minus 28t plus 22, which you'll want to factor. And our y double prime is 12t minus 28. And so we'll solve both of those to be equal to 0 and equal to undefined. All right, so when I factor, I'll take, let's see, a 2. That will leave me with 3t squared minus 14t plus 11. And then I try and factor that. See if any values, so 33 and negative 14. All right, so 33 is 3 and 11. So that is maybe good for me that would work out that way. So I could do negative 3 and negative 11. I'm going to run out of some room here. I think I'm going to have to erase my second derivative and move it down. Okay, so we'll have 2 times, all right, 3t and t. And then we're going to have minus 11 and minus 1. So my t values, when I set that equal to 0, I'm going to get t equal to 1, and I'm going to get t equal to 11/3. Now setting that equal to undefined is not necessary because this is a polynomial, and the polynomial will not produce any critical points at an undefined position. Okay, now we're ready to do the second derivative. So second derivative was 12t minus 28. We set that equal to 0. So t is 28 over 12. We reduce both of those by 4. We get 7/3. So the analysis chart you're going to create uses all 3 of those points in numerical order from least to greatest. So the smallest value is 1. And so we'll be looking at t less than 1. We'll be looking from 1 up to 7/3, which is the next one. We'll be looking at 7/3 up to 11/3, and then we'll be looking at greater than 11/3. And we are going to be looking at both the first derivative values and the second derivative values here. So I'm going to be looking at f prime, and I'm going to be comparing it to f double prime. When f prime changes, we'll have a max or min. When f double prime changes, we will have a point of inflection. And so I just need to find a value. When picking my one that's less than 1, I'm just going to pick 0 because that's the easiest. And I want to plug 0 both into, I'll take the number 0, I'm going to put it in here, and I'm going to put it in there. So 0 in the first derivative gives me 22, which is a positive number. And 0 in the second derivative gives me negative 28, which is a negative number. So I can tell that this is increasing with a curve that is sort of pulled downward. Okay, increasing with a curve that's bending in that downward direction. Something between 1 and 7/3, a nice one might be the number 2. If you plug the number 2 into the second derivative, that was easier for me. So that one is negative. If I plug the number 2 into the first derivative, I also get a negative number. The next one, let's see, the number 3 would work well for me there. If I plug the number 3 in, I still get negative in my first derivative, but I get positive in my second derivative. And then if I pick something bigger than 11/3, maybe like 10 or something like that, I get positive in both areas. What that analysis of the first and the second derivative will show you is where anything changes, like for example, from here to here, from there to there, there was a change from positive to negative. And then again, there was a change from negative to positive, but there was no change in the first derivative, at least, going on at 7/3. And then the only other change is from negative to positive at 7/3. So that helps you classify what's going on in each area. So you would say the function has a max where? Has a what? At where? Y. It has a what? A max. At where? 1. Why? Because what the first derivative did. Because f prime of x changed from positive to negative. Okay, so it's the what, the where, the why. Then we move on in numerical order to what's going on at, it's not x equals 1, is it? It's t. T. All right, the next one. The function has an inflection point. That's the what? At t equals 7/3. Because, and the reason for this one is going to be based on what the second derivative is doing, because f double prime of x changed from negative to positive. And then finally, your minimum is occurring at 11/3. So again, the what, the where, the why. The function has a min at t equals 11/3 because the first derivative changed. F prime of x changed from negative to positive. Otherwise, the function is continuous and differentiable, so there are no other critical points or points of inflection, or endpoints for that matter. Okay, any questions about the substance of that? If there were no, even if you get a second derivative value equal to 0 and you find one, but there's no change, it does not count as an inflection point. There has to be a demonstrated change for it to count as an inflection point. All right, one more example, and then we have an activity to do together. All right, our last example, same thing. We're going to find the critical points and inflection points for the following function. And this is f of x equals e to the negative x squared. So find the inflection points and the critical points for those. So do the calculus first. Find your f prime of x. Your f prime of x will be the derivative of an exponential, which is e to the negative x squared, times the natural log of e, times the derivative of negative x squared, which is negative 2x. So basically we get negative 2x e to the negative x squared. And then the second derivative is going to need me to do the product rule on that. And so I will group my equations into negative 2x as one part of the product and e to the negative x squared as the second part. And I'll do my derivative on that. So I'll start with e to the negative x squared. And then the derivative of negative 2x is negative 2. And then I'll add to that negative 2x. And the derivative of e to the negative x squared is, again, e to the negative x squared times negative 2x. So overall I have negative 2 e to the negative x squared plus 4x squared e to the negative x squared. I want to set my first and second derivatives equal to 0 and equal to undefined so that I can solve for my critical points and my inflection points. I think it'll be helpful to you in the first derivative for you to consider that as negative 2x over e to the negative x squared. I think it'll be easier for you to solve your math if you do rewrite that. So when you set that equal to 0 over 1, you'll also need to set that equal to 1 over 0. Okay, let's just do a little quick cross multiplication. We get negative 2x equals 0, so x is 0, so there's a critical point. On the other side, we get e to the negative x squared equals 0, which will never happen. An exponential function can never be equal to 0 because of the way exponential functions are shaped, and so I get no additional critical point values from that. That's the first derivative. What do you think I should do to the second derivative algebraically to help me out when I'm doing my solving here? Look at that second derivative. Is there anything you can do to that to simplify that? It's going to help your algebra a lot.
Yeah, you do the same thing where you put it in the denominator, so maybe you can
Yeah, even before I do that, I think I'm going to want to factor, because I notice that there's some stuff in common. And so if I take out e to the negative x squared, maybe even I take out the number 2 e to the x squared, that'll leave me with negative 1 plus 2x squared. It's going to be so much easier for me to solve this if I've written it in factored form. So that's going to give me 2e to the negative x squared in my it's going to give me, and I write it the right way, 2 times negative 1 plus 2x squared in my numerator, and then e to the negative x squared in my denominator. And I'll set that equal to 0 over 1. I'll also set that equal to 1 over 0. And we'll solve algebraically there. Cross multiply. When we cross multiply, we get 2 times the quantity, negative 1 plus 2x squared is equal to 0, which we can solve. When you divide both sides by 2, still equal to 0. When you add 1 to both sides, so x squared is equal to 1/2. And so x is equal to the plus or minus square root 2 over 2. For the undefined side, when we cross multiply there, we get the same thing we did the first time, which doesn't produce any additional values. So we got 0, and we have plus or minus rad 2 over 2. So your setup would go in order from smallest to largest. And so the smallest is the negative square root 2 over 2. And then the next one would be up to 0. And then 0 up to the positive square root 2 over 2. And then greater than square root 2 over 2. Then you'll want to pick some easy numbers that are going to make your math work out in your first and second derivative, f prime and f double prime. Okay, the rest of it is the same. Once you identify what's the pluses and what's the minuses, you can find your points of inflection and your maxes and mins by completing the chart. Just remember, the chart is super helpful. However, it doesn't get you any points. What gets you points is the statement of conclusion that you write after you've gotten the chart. All right, so with that in mind, we'll pause.